Okay, in this final video, what I'm going to be doing is I'm going to be teaching you how to linearize a nonlinear system so that we can use eigenvalue analysis to approximate the behavior around certain equilibria in a nonlinear system. So we're just going to do this by going right into an example. So let's get started. So let's start by supposing we have the nonlinear system where dx dt equals x squared plus y and dy dt equals xy plus x. Now we know and can already see that 0, 0 is already in equilibria because if you plug 0, 0 in, you're going to get 0 for all your solutions. But we need to find all our other solutions, so let's start by doing that. So to find our equilibria, you need to remember that you need to solve for where each function equals 0. We can go ahead and start by writing that x squared plus y equals 0, and we can write that xy plus x equals 0. Now, it's not really possible for us to solve x squared plus y equals 0 without any more information, but we can go ahead and take out an x in our second function, so we can go ahead and write that x times y plus 1 equals 0, and then we can definitely see that there's some equilibria values at where x equals 0 and where y equals -1. So then what we can do is we can take these values and we can plug them into this equation to find our equilibria points. So we'll start with where x equals 0. So when x equals 0, we know that y equals 0 as well, which is our 0, 0 equilibria. So then let's do y equals -1. So you have x squared plus -1 equals 0, and then you have x squared equals 1. And then when you take the square root, you get where x equals plus or minus 1. So that means that there are two more solutions for when y equals -1. So then that means that we have three equilibria altogether. We have our 0, 0 equilibria, we have an equilibria where x equals 1 and y equals -1, and then we have our third equilibria where x equals -1 and y equals -1 as well. Those are our equilibria. And now that we have our equilibria, we can actually go ahead and linearize our system. Since during linearization we'll be moving from a nonlinear system to a linear one, we are going to have new dx and dt terms. So therefore, what we have to do is we have to change our original nonlinear dx dt and dy dt terms into new functions. So now our original nonlinear functions will be labeled as f of x sub 0 y sub 0 for the dx dt equation and g of x sub 0 y sub 0 for the dy dt equation. And what these x sub 0 y sub 0s actually stand for is the equilibrium point which they are referring to. So depending on which equilibrium point we are using at the time that we are inputting values, these x sub 0 y sub 0 values will just be based upon the equilibria. And now we have our actual equation to linearize our nonlinear function. So now what we have is our new dx dt and our new dy dt are laid out for us. They are right here. So these belong to the linear set. And then what happens is that our new dx dt is equal to the partial derivative of our f of x sub 0 y sub 0 function with respect to x times x plus the partial derivative of that same function with respect to y times y. And then the same thing is done to find our dy dt, except we use the g of x sub 0 y sub 0 function instead. So now that I've kind of laid down how we actually go about doing this, I think the best way for us to get stuff done is to actually start finding our partial derivatives. So let's start by finding our partial derivative with respect to x and y of our f of x sub 0 y sub 0 function. So we know that our original f of x sub 0 y sub 0 is equal to x squared plus y, and we know how to take partial derivatives from our last video, so then we can go ahead and just do that. So we know our df dx with respect to x is equal to 2x, and then we know that our df dy is equal to just 1. And then we can go ahead and find our partial derivatives of g of x sub 0 y sub 0 with respect to x and y as well. So we know that our original g of x sub 0 y sub 0 is equal to xy plus x. So then we can go ahead and take our partial derivative. So our dg dx with respect to x is equal to y plus 1. And then we can say that our dg dy with respect to y is equal to x plus 0, or just x in this case. And then we have all of our different parts which we can use for our linearization equation, which we can plug in. So from all the partial derivatives, we now know what our new dx dt and our new dy dt is in our linear system. So we can just go ahead and write those up at the top so that we can remember them whenever we're working with our different equilibria. So we know that our dx dt is now equal to 2 times x sub 0, which is one of our equilibria points, times x plus y. And then we know our dy dt is equal to y sub 0 plus 1 times x plus x sub 0 times y. So now that we have those, we can go ahead and plug in any equilibria from the original functions and obtain a linear system and perform eigenvalue analysis on that system so we can classify the equilibria itself. So then we can go ahead and start with 0, 0. Now that we know the individual formulas for each of our functions, we can just go ahead and plug in our equilibria 0, 0. So we can say that dx dt equals 2 times 0, which is 0, times x, which is still 0, and then just plus y, so that's y. And we know our dy dt is equal to 0 plus 1, which is 1 times x, so that equals x, plus 0 times y, which is 0, so it's just x. So then what we can do from there is we can use this information and plug it into our eigenvalue formula as well. So then we can say our lambda plus or minus equals 0 plus or minus the square root of 0 plus 4 times 1 times 1. And you know that comes from the a plus d plus or minus the square root of a minus d plus 4bc, and then it's all over 2. So then when simplified, we can go ahead and say that's equal to plus or minus the square root of 4 over 2. So then you know it is equal to plus or minus 1. So then we know that since there's opposing signs, 0, 0 has to be a saddle. Okay, so now that we've figured out what type of equilibria 0, 0 is, we can focus now on 1, negative 1. So since we already have our formula to find our new linear system up top, we can go ahead and plug in our equilibria values. So we've got 2 times our x value, which is 2 times 1. So that would just be 2x. So our dx dt equals 2x plus y. And then our dy dt is equal to our y value plus 1, so that would be negative 1 plus 1, so that's 0x, plus our x value, which is just y. Now we can go ahead and use these values to plug into our eigenvalue formula to figure out our type of equilibrium. So then we're going to go ahead and plug these in. So our A is 2, our B is 1, our C is 0, and our D is 1. So you have your lambda plus or minus equals 2 plus 1 plus or minus the square root of a minus d, which is 2 minus 1, which is just 1 squared, plus 4 times b, which is 1, times c, which is 0. So then you have all that over 2. So then you know that this equals 3 plus or minus the square root of 1 over 2. So it's 3 plus or minus 1 over 2 essentially. So then you either have an answer of 2 or 1. So then since both of our values for our lambda plus or minus are greater than 0, we can go ahead and say that we know this is a source equilibria and that it is repelling and unstable. And now we can move on to our final equilibria of negative 1, negative 1. So we can go ahead and plug in our values using our formula shown up at the top. So you get our dx dt and our dy dt for our linear system. So our dx dt is going to be equal to 2 times negative 1, which is equal to negative 2. So it'll be negative 2x plus y. And then we have our dy dt, which is equal to our y value, negative 1 plus 1, which is 0, times x, which is 0, plus our x value, which is negative 1 times y, so that'd be negative y. So then our a value with this is equal to negative 2, our b is 1, our c is 0, and our d is negative 1. And then we can go ahead and use these values once again to plug into our eigenvalue formula. So then we can go ahead and say that our lambda plus or minus is equal to a plus d, so it would be negative 2 plus negative 1, which is negative 3, plus or minus the square root of a minus d, which is negative 2 plus 1, which is just equal to negative 1, so it's negative 1 squared, plus 4 times b, which is 1, times c, which is 0, all over 2. And then we can go ahead and simplify and say that negative 3 plus or minus the square root of 1 over 2. So it's basically the same as last time, except this time we're going to get the values of negative 2 or negative 1. So then since both of our values for lambda plus and minus are below 0, we know that this is definitely a sinc equilibria. So we know then that our original nonlinear function has 3 equilibria with 3 different types of behavior. They have an equilibria of 0, 0, which is a saddle, an equilibria of 1, negative 1, which is a source, and an equilibria of negative 1, negative 1, which is a sinc. Alright, and that is how you do linearization and eigenvalue analysis, and I hope you learned everything that you need to learn, and that this was very helpful.